So this.
Don't worry about that. We can't see that. As long as it's not blocking for you, don't worry about it. Yeah.
Okay. Sorry, that was my computer decided to start speaking because it was on a YouTube thing, but we should be good to go now. We're streaming, and welcome to everybody on the stream. And I'm recording. So Steph, I will turn it over to you. And if you're not speaking, if you'd please mute your microphone, that would be appreciated.
All right. All right. Thanks, Pete. Thank you, everybody, for joining. I am very excited to introduce Angelica Soria. Angelica will be presenting her master's thesis work. So a little bit about her. She started her master's in fall 2019. This is when she joined my group, my very first student. So that's exciting. Prior to her time here, she received her Bachelor of Science from the University of Missouri, where she majored in atmospheric science. And during her time there, she first volunteered with the National Weather Service in Topeka, Kansas, where she did some research on flash flooding. And I mentioned that because she is now, since March, working as a full-time meteorologist at the National Weather Service office in Brownsville, Texas. So that's right along the Mexico-Texas border. So while a lot of her probably concerns over these past few months and next several months are on tropical cyclones, her master's thesis is actually on extratropical cyclones and how their paths are influenced by the Madden-Julian oscillation and its teleconnections. So thank you so much, Angelica, and I'll let you go ahead and share your screen. And while she's setting that up, I will mention, please hold your questions until the very end of her talk. And then once her talk is done, you will be able to either raise your hands for questions or you can also type your questions into the chat and I will monitor those. All right, thank you, Angelica. Go ahead and take it away.
Okay. Hi, everybody. Thank you for coming to my thesis talk today. The title of my thesis is MJO teleconnection patterns and their effect on extratropical cyclone activity in the mid-latitudes. And then, of course, Stephanie Henderson was my awesome advisor. So I'm just going to start out with just a little bit of background about what is the Madden-Julian oscillation exactly. So the MJO is an oscillation in the tropics centered around the equator. It's composed of 8 phases, which represent its location in the ocean. And it takes about 30 to 60 days to travel from the Western Indian Ocean to the Western Pacific Ocean. And it moves at about 5 meters per second, and it does vary seasonally and interannually. And referring to the figure on the right, there is a lot of ongoing research regarding the MJO dynamics, but what we know right now is that it is a couplet of Kelvin waves and Rossby waves, and that the low level intensity of the Kelvin wave easterlies and the Rossby wave westerlies determine the MJO's phase speed. And so looking at the figure on the right that I got from NOAA, we can see that there is a constant overturning circulation that brings convergence at the surface, which will create stormy and wet conditions, and then also divergence at the surface a little further to the east that will create sunny and dry conditions. And again, this is situated about 30 degrees east and 150 degrees west. And moving on to this cool graphic. So this is a good representation of the MJO's variability and its movement throughout the 8 phases. And so this shows MJO cycle precipitation anomalies from the tropical rainfall measuring mission data set, so the TRIM. And the thick, solid, and dashed contours outline the main regions of enhanced and suppressed MJO rainfall from the CPC merged analysis of precipitation data set, so CMAP. So one thing to focus on before I run it again is looking at the top right of this figure. We can see that there's RMM phase 1 through 8, and it starts out at day 0 and it goes through day 48. So when I press play again, we can see the blue colors represent more rain and then the red or less rain. So we can see that as the MJO moves throughout time and goes through its cycles, that the precipitation rate does change as those phases move forward. So just watch it one more time. So again, just a good visualization of how the MJO's variability does change throughout its 8 phases and as it moves through time, which can make doing research on it a little interesting and not always tell a complete story just because it is so variable. So we know that the MJO has variability, but how do we track it? So the MJO is measured in several different ways, but most commonly is measured by RMM or OLR indices. So the RMM is the real-time multivariate index, and the OLR is the outgoing long-wave radiation index. I took this screenshot on the right. This is the RMM. This is the RMM way to measure it, and this is from April 19th, 2021 through May 28th of 2021. And the 8 phases show each location, and the line reads in a counterclockwise direction, and the different colors in the line represent the different months. So in this case, green stood for April and blue represented May. And the numbers on the line represent daily indices. And the unit circle in the middle represents the strength of an MJO event. So if the line is outside the unit circle, it actually shows that that's a strong MJO event. So for example, in the beginning of May in phase 1, we can see that that line is really far away from the unit circle. So that is shows a very strong MJO event, as opposed to phase 2 and 3. That line is still outside the unit circle. So it's still a strong MJO event, but not as strong as it was in phase 1. So now that we have a little bit of background on the MJO, now it's time to move on to my motivation for my research. So first off, I wanted to understand, how do teleconnection patterns work? And also, how do the teleconnection patterns behave during the springtime? So currently there is research done on teleconnection patterns at this time, but it is mostly done during boreal winter, because that is when the teleconnection patterns are the strongest. But they are also present throughout the rest of the 4 seasons. So I chose the springtime, and the months I have for that are March, April, May, and June. And so next question I would ask myself, do the MJO's teleconnection patterns have an effect on where severe weather occurs in North America? Since this will be during the springtime. And if it does, how is the large scale circulation modulated to create more favorable environments for severe weather events to occur? And so I just wanted to think about how severe weather and large scale circulation are hard to connect. So I wanted to see if I could measure that in a way that would make the most sense to me. So I started looking at extratropical cyclone frequency and intensity to help piece together my questions that I had. So first off, how do teleconnection patterns work? And using this picture on the right from the Subseasonal to Seasonal Prediction Task Force, it's a good representation of how the MJO's convection can have an influence on the large scale circulation, and then in turn influences the rest of the globe. So it can take about 2 weeks for North America to see the effects of the MJO's convection. And just a few of these teleconnection pattern impacts are the location of the subtropical jet stream, the modulation of extratropical storm tracks, Rossby wave breaking, the PNA, NAO, and AO as well. So we can see that teleconnection patterns affect the large scale dynamics, which will in turn then change the synoptic and mesoscale dynamics as well. So looking at this picture on the right, we can see that on the left side of the picture, we have the MJO's convection and the little cloud and the rain. And following the gray dots across the rest of the globe, we can see how the large scale circulation may be modified. So the green line that goes through the entire picture is Rossby. It represents Rossby wave breaking, which, and then looking at the North America on the right, that could lead to blocking, heat waves, and then also maybe help to start atmospheric rivers. And then also looking just to the right of the MJO convection, we have in these little comma shapes storm tracks, which is what I'll be looking at. But then also, good thing to know, moving all the way to the right side of this picture, we have tropical cyclones as well. So the MJO does have a effect on the large scale circulation, which then will affect many things, even all the way across into the Atlantic Ocean. So first off, I needed to find a methodology that helped me to understand how these extratropical cyclone tracks were being modulated. So I reached out to Kevin Hodges and asked permission to use his tracking algorithm. And his tracking algorithm was applied to daily mean sea level pressure data from the ERA5 reanalysis. And the daily data is separated into 3 hourly time steps. And there are certain constraints that were applied to the MSLP values for filtering purposes. There's an upper bound displacement constraint, a velocity constraint, and a track smoothness constraint. And just looking at the picture that I have on the right here, this is just a screenshot that I took just to show everybody what the raw data actually looked like. And so these are cyclone tracks for my spring season, which is March, April, May, and June, just of the year 2019. So as you can see, it's a little messy and kind of hard to read through or to kind of pick through different cyclone tracks and then also individual cyclones. So that's why those constraints were there to help organize it a little bit better and help separate some of the tracks from one another. So similar minimum mean sea level pressures were linked together, and the separation of those tracks was determined by changes in velocity. And next, there were text files that were created containing the cyclone's track length, intensity, latitude, and longitude coordinates. And then also some other constraints within the tracking algorithm was that the velocity of the storm had to be present in at least 3 time steps per day. And the cyclones that were shorter than 2 days, that moved less than 5 degrees per day, or were less intense than 13 times 10 to the negative 5 per second, were not included. So just to only include significant cyclones in this process, since as you can see, just looking at 2019, there was a lot of data to filter through. Next, I used the March, April, May, and June 300 hectopascal zonal wind from 1981 to 2010 from INCEP and CAR. And I just wanted to include this figure for reference for the MJO-driven anomalies, just to see how the anomalies departed from the mean climatological jet. And so this was really helpful in looking at my 500 geopotential height anomalies that I created and just seeing, kind of putting together the story of why the frequencies or the intensities did what they did. So it was just a good reference. And so you will see this figure through the rest of my talk as well. So next I did 500 geopotential height composites, and I I found the anomalies and I composited them by MJO phase, and I calculated them during MAMJ of 1979 to 2019. And then I conducted a 2-tailed student's t-test at the 95% significance level, which is shown by the stippling in the next slide. So here on this next slide, I have phases 1 through 8, and the reddish orange colors represent the positive geopotential height anomalies, and then the bluish colors represent the negative geopotential height anomalies. And so the negative are troughs, and then the positive are ridges. And so as you can see, I have all 8 here. But I only have so much time in this presentation, so I don't actually go through all 8 phases of the MJO. I just picked a few to go over and compare them to each other. And so I will first go through phase 1, and then I group together phase 3, 4, and 5, and then I will go through phase 8. And so it was just easier to pick a few and to do those because I wouldn't have time to go through all 8 phases. So next, the data and methods for the cyclone frequency. So first off, I compiled the daily cyclone tracking algorithm data into 3 hourly data. And then the daily data is used to find the count of the cyclones per grid box per day. So then I created a dichotomous index so that if at least one time step contained a cyclone, it counted as 1 count. Otherwise, it was labeled as 0. And so this was done so that the same cyclone wasn't counted more than once, because that would have really messed up my frequency. And so we just needed a simple index to where I wasn't counting the same cyclone over and over again. So the daily dichotomous index was conducted for 1979 to 2019. And then I composited by MJO phase using RMM indices. And the mean cyclone frequency is computed by summing cyclone counts and dividing by the total number of days in the spring season over all the 40 years. And then I multiplied that by 100 to get a percentage. And then the cyclone frequencies were found by subtracting the mean frequency. And this is my mean frequency that I computed. So it's the cyclone frequency climatology. And again, this is for 1979 through 2019 MAMJ. And the highest frequency is about at 6% in this figure. So that happens to be off the east coast of Asia near Japan, over the Western Atlantic Ocean, and near the Rocky Mountains. And one thing that I found really interesting when computing the frequency climatology is that it actually picked up on a higher frequency in the central United States, which is about the area where the Rocky Mountains would be located. So this would suggest lee-side subsidence in that area. But I thought it was pretty cool that the frequency climatology picked up on that. Even if it's just those small red pixels, it still did pick up on that. So first off, comparing cyclone frequency climatology to the climatological jet, we can see that the areas of highest cyclone frequency match the areas of highest zonal wind. And that's good. It shows that my cyclone frequency climatology matched the climatological jet, so that match. So it suggests that cyclogenesis occurs over areas with large wind shear. So like I said, we have off the east coast of Asia where we have higher cyclone frequencies, and then looking at the climatological jet on the right, that is where jet max is located as well. And then looking over the eastern half of the United States, we can see a smaller jet streak in the green and yellow colors. And then we also have higher values of cyclone frequency in that area as well, off the northeast coast of North America. So it's just good to have it as a reference to check to make sure that my plots and that my findings were aligning to where they should be. Next up is my cyclone frequency anomalies. And again, these were composited by MJO phases for 1979 through 2019 of March, April, May, June. And looking at all 8 of these phases, they the red colors represent the highest it would go up to would be about 2%, and then the lowest is about -2%. And so the red colors are for above average cyclone frequency, and the blue colors are for below average cyclone frequency. So I'm going to start out with phase 1. And this is the cyclone frequency versus the cyclone frequency climatology, just to see its departure from climatology and really make the anomalies stand out, especially as I'm trying to analyze it. It really helps when I compare the two. So at first, looking at phase 1 on the left, the northeast coast is above normal. We can see by the red values there. And then looking at the central United States, the central US is below normal. And then looking at the North Central Pacific, it happens to be above normal. We can see those redder colors there in the middle as well. So just looking at phase 1, we can see that those areas that I outlined in the red circles are greater than the cyclone frequency climatology, and they are a departure from the mean. So next next step would be to try to figure out why that is. So that's when I included my 500 geopotential height composites. And at first, there is looking at phase 1 on the right, there's a positive geopotential height anomaly over northern Canada. And then there's also a negative geopotential height anomaly near the Bering Strait. So it's very interesting to compare these two next to each other, because if you look closely on the left side, on phase 1, we can see that where that negative geopotential height anomaly would be situated in the North Central Pacific, there's actually red values on either side of that trough. So I thought that was very interesting to look at. And then comparing the cyclone frequency phase 1 to the climatological jet, the west-east 500 geopotential height dipoles modulate the placement of the jet. So the positive geopotential height anomaly can be expected to alter the cyclone tracks away from the central United States. So looking at this figure on the left in phase 1, we can see, like I mentioned earlier, there's blue in the central United States, where looking at the climatology figure, there should be at least above normal cyclone frequency in that area. So it could be expected that the ridge that would be settled over the Canada area east of Alaska would maybe be perhaps keeping the cyclone tracks away from dipping down into that northern border of the United States, southern Canada. And then again, I mentioned the negative geopotential height anomaly that's situated in north central Pacific that would also could be the reason why there are small indications of above average cyclone frequency to the left and right of the trough. So moving on to the phases I grouped together, which is phases 3, 4, and 5, and comparing that to cyclone frequency climatology. First up, looking at phase 3, which is the top figure, we can see that there's above normal cyclone frequency in the southern United States and north central Pacific, as well as below normal frequency near the Labrador Sea. And then phase 4 looks similar to phase 3. Some of the cyclone frequency anomalies aren't as intense, but it looks about the same. It's not until we go to phase 5 where we see there's actually below normal cyclone frequency anomalies in the north central Pacific. So very interesting to see the departure from the frequency climatology on the right, where we have in phases 3 and 4 above normal cyclone frequency, but then that by phase 5 that turns into below normal cyclone frequency in that area, which is also a departure from the mean. So just interesting to compare that to what normally would happen. So to, again, try to piece together why this is happening, looking at phases 3, 4, and 5 of the 500 geopotential height composites, we can see that starting at phase 3, there's a positive geopotential height anomaly in the central Pacific and a negative geopotential height anomaly in the central United States. And then moving to phase 4, there's a positive geopotential height anomaly, but it's moved slightly to the east. And then moving on to phase 5, there's that same positive geopotential height anomaly, but moved further to the east. And that is the main reason why I grouped together phases 3, 4, and 5, is because I saw that same positive geopotential height anomaly just moved slightly further east as we went through time. So I thought that was pretty interesting and that I should group those together because it might tell a more complete story if I group together phases 3, 4, and 5. So looking at the cyclone frequency plots on the left, starting out with phase 3, we can see that at first there is above normal cyclone frequency in the north central Pacific, but as we move further throughout time by phase 5, it actually is below normal cyclone frequency. And my thoughts were on that the ridge that was situated in the central Pacific may have, if it sat in the central Pacific long enough, it may have an impact on the large scale flow to where it actually alters the cyclone tracks to where it's actually below normal instead of above normal. And so comparing the cyclone frequency to the climatological jet, cyclogenesis typically occurs on the left exit region of the jet, which would be near the Bering Strait in the climatology figure. But positive geopotential height anomaly may work to inhibit a favorable environment for cyclone activity to occur. So it's just very interesting that throughout time that those anomalies completely change to being negative or below average when looking at the Central Pacific area. And I put a red circle on the climatological jet because in that left exit region, we would expect to see above average cyclone frequency. But as we move throughout time, if we have a ridge situated in that area, it may mean that it will eventually go towards below average cyclone frequency. And then moving on to phase 8, cyclone frequency versus cyclone frequency climatology. looking at the red circle on the left figure, we have negative frequency anomalies near the Labrador Sea, which is the negative, or which is the bluer colors. And then moving on to the Central Pacific, the North Central Pacific, we also have negative frequency anomalies over there as well. So again, both of these are departures from the mean when comparing to the figure on the right, when they're blue, so they're actually below normal cyclone frequencies. And then we move on to the cyclone frequency versus the 500 geopotential height composite. And we can see that there is a negative geopotential height anomaly in the North Central Pacific. And so that sticks out and may be the reason why for phase 8, when looking in the North Central Pacific, we have below average cyclone frequency in that area. The trough may actually alter the cyclone tracks further south instead of where they would actually be above normal, or normally would be in the North Central Pacific, but it may shift the activity further south. And so it's good to refer to the climatological jet in this sense and see, or to understand what that trough could be doing to the large scale flow. So the counterclockwise flow disrupts the large scale circulation enough to possibly suppress cyclone activity in the North Central Pacific. And the negative geopotential height anomaly is expected to shift the jet slightly southward then, and which is very interesting because we would normally have cyclone activity in that area, but in this case we have the bluer values. So just interesting to see that that huge trough that appears in phase 8 could alter the cyclone frequency enough to where the tracks actually don't move through the area that they are typically used to traveling through. So next up is the cyclone intensity that I computed. And the intensity was computed similarly to the frequency in regards to getting the daily cyclone tracking algorithm data prepped to 3 hourly data. And then I created a daily dichotomous index again. And then the sum of the daily intensities was divided by the counts of the daily cyclone intensities to get the average cyclone intensity per day. And then I computed that average for all the 40 years and then composited them by the MJO phase using the RMM indices. And then the average cyclone intensity anomalies were computed by subtracting the mean intensity. And then the units of cyclone intensity, vorticity are based off of mean sea level pressure, just as a reference as I go through my intensity figures. This is my cyclone intensity climatology figure. And again, this was computed for 1979 through 2019 of March, April, May, and June, so my spring season. And then just to compare it to, compare my intensities to the climatological jet, we can see that there are areas of highest cyclone intensity that are located in the Northern Pacific, just north of where the jet max is located when we look at the jet figure on the right. So good to remember and interesting to point out. And then also there are a high value, or there is higher cyclone intensity in the Northern Atlantic Ocean as well. And this would suggest that the most intense cyclone intensity occurs just east of the jet max in the exit region. And these reddish colors sit at about 25 to 30 times 10 to the negative 5 per second, just for reference. And then again, so I put a little red circle on where the east of the jet max in the exit region would be. So here are my cyclone intensity anomalies, and I computed them from 1979 through 2019 for MAMJ and composited them by all 8 MJO phases. And again, looking at the phases, the red colors represent the above average cyclone intensity anomalies, and then the blue represents the below average cyclone intensities anomalies. And again, I'm going to go through phase 1, and then I'll go through phases 3, 4, and 5, and then I'll go through phase 8 again. So first up is phase 1 and comparing the cyclone intensity to the cyclone intensity climatology to see again how it departs from the mean. And first up is this small red dot, which is a positive intensity anomaly off the Northwest Pacific coast. And then also just moving slightly west, there is a negative intensity anomaly in the eastern central Pacific. So those are two interesting anomalies to point out. So to try to understand why that's happening, we need to compare it to the 500 geopotential height composites to get a clearer picture. And so starting out with phase 1 on the right, we can see there's a positive geopotential height anomaly over northern Canada, and then a negative geopotential height anomaly near the Bering Strait, which is, I showed this figure earlier, but it's just good to have as a reminder because now we're looking at a different variable. We're looking at cyclone intensity. And so it's interesting to see how, looking at my intensity figure on the left, that small area or the small anomaly, the above cyclone intensity or above average cyclone intensity, the red dot off the Northwest coast, happens to be just south of where that dipole is actually located. And then just slightly further to the west, there are negative intensity anomalies. So just looking at this, we do have a small dipole effect. So that could suggest why there are some below or an area of negative intensity anomalies and then positive intensity anomalies. And so kind of explain that in this next slide, where I have the intensity versus the climatological jet. The west and east 500 geopotential height dipoles could be expected to modulate the placement of the jet, like I had mentioned while looking at the cyclone frequency. But the dipole can be expected to create an area of strong vertical wind shear in between it, which possibly suggests that small area just to the south of the dipole to be an area favorable for positive cyclone intensity anomalies. And also, and in turn, just a little bit to the west, create an area where there's below average cyclone intensity, so negative intensity anomalies, because that's about where the trough would be located. So it's just interesting to see that that there is just that small little cyclone intensity, but it does actually happen to be straight a little bit to the south and in between that west to east dipole. So next, moving to phases 3, 4, and 5 of cyclone intensity, and then comparing that to the cyclone intensity climatology. Starting out with phase 3, we can see that the positive intensity anomalies appear down the east coast of the United States. And then moving on to phase 4, we can see there's a negative intensity anomaly near the Bering Strait. And then moving to phase 5, we also still have the presence of that negative intensity anomaly. And it's not as organized or as strong as it is in phase 4, but it is still there in phase 5. And the intensity figures overall were a little bit harder to read just because they are a little bit more noisy than the frequencies were. So comparing the intensities to the 500 geopotential height composites, just as a reminder, phase 3 features a positive geopotential height anomaly in the Central Pacific and a negative geopotential height anomaly in the Central United States. And then phase 4 has that same positive geopotential height anomaly, but moved slightly east. And then phase 5 is that same positive geopotential height anomaly, but moved a little further to the east. So in comparing to the cyclone intensities on the left-hand side, we can start to piece together why the anomalies are where they are. So starting out with phase 3, the positive intensity anomaly down the east coast of the US, I thought was interesting because looking at climatology in the past couple slides, we can see that there is above average cyclone intensity happening all the way down the east coast of the United States, which is a departure from the mean because it doesn't really go that far down south. So it's interesting because looking at phase 3, we can see that there is a negative geopotential height anomaly situated in that area. So that could possibly be the reason why there is an increase in the positive intensity anomalies just off the east coast of the United States. And then moving to phase 4, we can see that that geopotential height anomaly, or the positive geopotential height anomaly, does create a little bit of issue for these cyclone intensities. At first, we do have some above average cyclone intensity, some red colors in the North Central Pacific, but eventually moving on to phase 5, those turn slightly bluer. So just, it speaks the same as when I was referring to the cyclone frequency, that if that ridge sits in the North Central Pacific long enough, it will have an impact on cyclone frequency and cyclone intensity as well, to where they start to become possibly even below average what they normally are. So again, comparing the cyclone intensity phases 3, 4, and 5 to the climatological jet, the positive and negative geopotential height anomaly do affect the curvature of the jet and the large scale flow when referring to phase 3. And so the curvature of the jet may affect maybe the reason why there is above average cyclone intensities in phase 3. So why we see all those red dots. And then phases 4 and 5, the positive geopotential height anomaly works to inhibit a favorable environment for the positive cyclone intensity just to its north, which would be in the Bering Strait area. Because as we can see, phase 4 in the Bering Strait area, like I said earlier, we have those negative cyclone intensity values, and then we also see them still in phase 5. But like I said, it's gradual, it's small, but it's there. Just looking at the colors and the values of the cyclone intensities, that they do eventually turn bluer by phase 5. So looking at phase 8, and in the cyclone intensity versus cyclone intensity climatology, we can see that there is a positive intensity anomaly situated in the East Central Pacific, and that would be a departure from the mean because it is a positive intensity anomaly, and it is a little further south than where we would expect to see it as well. And then comparing the cyclone intensity to the 500 geopotential height composite, again, there is that negative geopotential height anomaly in the North Central Pacific. And I thought it was interesting that just to the east of this trough, we have a small area in phase 8 that is a positive intensity anomaly. So just coming so the trough might create an area of larger or of higher cyclone or above average cyclone intensity just to the east of it. And again, it's good to refer to the climatological jet to see what that trough is actually doing to the large scale flow. And so the climatology suggests that the most intense cyclone intensity occurs east of the jet max in the exit region, which is what I said earlier. But due to the placement of the negative geopotential height anomaly in the Central Pacific, could possibly expect a southward shift to the jet due to where the trough is located. And that's where the dotted circle is. And that is where we have a slight increase in positive intensity anomaly, is just a little further south than where we would expect it looking at the climatology. So I thought that was very interesting that that trough could just affect the jet just slightly enough to where the most intense cyclones aren't situated in the North Central Pacific, but actually more off or more near the Northwest Pacific of the United States. So for my conclusion, examining the 500 geopotential heights, cyclone frequency, and cyclone intensity in unison gives insight into how the large-scale dynamics are affected by MJO teleconnection patterns. And the phases discussed strongly suggest that the MJO changes the large-scale circulation during MAMJ through teleconnection patterns. So we can expect that the teleconnection patterns do change the intensity and location of the storm tracks by changing the intensity and direction of the flow. So applying the results from the study can be beneficial in improving the predictability gap in the subseasonal timescales. So that just means that the monitoring of the MJO would be of significant interest to forecasters due to the fact that its teleconnection patterns do affect our large-scale dynamics by modulating the large-scale flow, and in turn will change extratropical cyclone tracks and cyclone intensity. Some of the future work that could be added to this project would be to try to analyze moisture transport associated with the spring MJO teleconnection patterns using total column water vapor. There is a few papers that I read while doing my research that did actually use moisture transport, which I think would help to give a better understanding of the large scale flow and what actually goes on. So I think that'd be interesting to add in the moisture aspect of it, because that tells a whole different side of the story when it comes to the MJO. And then also use a different method besides the Kevin Hodges tracking algorithm to track cyclone behavior. Again, in some previous work that I've read, there was some eddy variance methodology that some authors were using, and I thought that could be interesting to pair with the results I already have to see if they match or if they disagree or things like that, or just back up the findings that I already had. So that would be interesting to just do a different method. And then also consider more geopotential height levels such as 250 and 800 geopotential heights to see the teleconnection patterns throughout the depth of the atmosphere. Because right now I only did the 500 height level, and it'd be interesting to get 250 and 800 again to just get a more complete, just for completeness, just to see if the anomalies do still appear at 250 and at 800, and or if they're as strong as they were at 500 as well. So that would be interesting to look at different levels. And then to also compute lags for all the MJO phases. Again, that would just help give a more complete story, and lags help you see the movement of the MJO throughout time better, and answer some of the questions that may still linger after my current research. So lags would definitely be helpful for that. So in my acknowledgements, I want to thank my master's committee, Stephanie, John, and Angel. Thank you for coming and watching, and for all your help that you guys gave to me. And then also I want to thank Kevin Hodges for letting me use his tracking algorithm. He helped me so much in learning how to use it. It was very complicated. And Pete also helped me a lot in trying to figure out the algorithm. And then extra special thanks to my advisor, Stephanie Henderson, for working with me through a pandemic that was not easy, and while I worked a full-time job, and none of this research would have been possible without her support and guidance. And thank you to one of my best friends at AOS, Gerald Acton, for all the coding help. I truly could not have made the plots look as pretty without him, or any of the coding. He helped me so much. And then thank you to my amazing friend group at AOS. The study sessions in the conference room on the 14th floor were so terrible, but they were so worth it. And if you saw that the conference room was full on the 14th floor, it was probably us studying or working on something. So, and then thank you to my friends and family. I have a super great support system, and I couldn't have done any of this without everybody's help. So thank you guys for coming to listen to my presentation today. It was a long road, but I made it. So thank you.
Great, thank you so much, Angelica, for that great presentation. So we will now open up the floor for questions. If you have a question, you can either type it into the chat or you can raise your hand. And to just ask your question, just make sure you unmute your mic before you ask your question. And Pete, let me know if you get any questions on the YouTube stream. So does anybody have any questions? John, go ahead.
Yes, Angelica, this was an excellent presentation. I thought it was well thought out. It reflects changes I think you've made to your document since I made comments on it. I think you really spent a lot of time thinking about what you're looking at and what you've been researching. So congratulations on that.
Thank
I
you.
had a couple of questions. I'll just ask one. I think it's a great idea to combine both the track variations as well as intensity variations that you did. But I've seen so many figures that look like the ones you have, sort of splotchy with regard to blue and red spots of your cyclone intensity differences. And it was true also for tracks, but I especially had an idea about the cyclone intensity differences. And the thing that it reminded me of was looking at raw Q vector convergence and trying to intuit from that what the inversion of the omega equation would actually give you back. And that's the analogy here that I think you might be able to use. And it's along the lines of one of the things you suggested yourself. Del squared of the geopotential height perturbation is the geostrophic vorticity perturbation. And so you've got a del squared of a known quantity equals something that you can plot. And you're plotting, you could plot the geopotential of the geostrophic vorticity perturbation as a measure of intensity difference. And in fact, maybe Hodges does that. But then if you think about looking at the companion geopotential height anomalies at the level at which you're looking at the intensity, you've already done the inversion because it's already, that's what it is. Del squared phi prime equals eta prime. So that might give you less splotchy, but just as insightful results, might make it easier for you to convey to, because I think it's clear you've thought about what those little just mean. You have some good idea what they mean, but it might be even easier for you to convey them if you went to like 1,000 millibar or 950 millibar geopotential height anomaly instead of cyclone intensity anomaly, because they're roughly the same thing and they're linked by an inversion which will smooth it.
Yeah, no, that makes sense. You're bringing it all back to me.
Sorry to do that to you.
No, it's okay. I know, I was like, I haven't been in your class and I don't know how long, but no, that, yeah, it's all coming back. No, that would make sense. That would be kind of cool to look at. Like, obviously I like didn't have like a lot of time to like do more. I wanted to do more with it. I just like didn't have time because I thought I did actually find some really cool conclusions that came from this. But looking at omegas, it would just complete it a little bit more and give, like I said, more background into why these things are happening and how the large scale flow is actually being altered.
Yeah, I'm just thinking of geopotential height perturbations as opposed to cyclone intensity perturbations as you measured them. That might be another way to convey where the areas of interest are, I mean, with respect to the various phases. So nice job.
Thank you.
Any other questions?
We do have one question from YouTube. Evan Meeker asks, did you calculate the statistical significance of the cyclone frequency anomalies during the different MJO phases?
I didn't do the statistical significance of it. No, those were just intensities, or they were, sorry, anomalies. So they were subtracted from the mean. So I don't know. I didn't do like what I did with the geopotential height anomalies where I ran like the statistical analysis on it. But I did subtract the mean to see what were the most significant. So I don't know, but I didn't do a stats test on it, but I did subtract the mean. I don't know if that makes sense. Sorry.
Go ahead, Liz. I see your hand is up.
Okay, I'll turn everything on and put my hand down, and that just took the wind out of half of my question right there. Hi. So my question was, yeah, a lot of that looks really splotchy.
I know.
That's the way data is. Don't worry.
Yeah,
That's the way life goes sometimes. So my question more is, have you thought about, in a way, how meaningful are those splotches? So in a percentage of, say, the normal geopotential height anomalies, can you figure out like that intensity, how much of a dip is that from the normal dips that go by? Is there some way of like percentaging it out? Like, is it a 10% deviation or a 20%, something along those lines?
Yeah, that'd be kind of cool actually, to see, because like, yes, I can see it, but also how significant is it? Like, we're just looking at like comparing like just face value, but like if I actually ran like some stats on it, it would actually give me some numbers that would say, yeah, we can see it's a departure from the mean, but how much above or below is it? So I get what you're saying, which again takes me back to your class. And so I'm like, it's all coming back. But I did the students T test based on some of the notebooks we did in class. So just know I owe that one to you. So, but no, yeah, you're right. I did not do that, but that would be kind of cool to look at to see how like departed it was from the actual mean. But yeah, I just didn't get to run as much stats as I wanted to on this. I just didn't have it as I ran out of time. But that would be kind of cool to see like how big of a departure it was, other than just like face value, because the intensities were very splotchy. So
Go ahead, Maria.
Hey, great job. It's really interesting stuff. I may have missed, did you say that you filtered by strong MJO events?
yeah, I don't know if that was on my slide, but yes, I did.
Okay, was it just the one standard?
Yeah, mhm,
Okay.
exactly. Yep.
I'd be curious. I was curious just like how many were kind of in each of those in your composites. And
I know I got that comment when I did the practice run through. I think Nuo mentioned it, like how many cycle, like when I separated it out into phases, how many were there per phase. And I would have loved to add that in there, but I ran out of time. But that's a good point though. That would be cool to add too, just to see like, okay, in phase 1, we're only looking at like 100, and then phase 2 we're looking at like 150, so it makes a difference. But I didn't do that, but you're right, that would be very interesting to add.
Go ahead, Larissa. I think you're next.
I was just nice talk. So it was really interesting. I was especially intrigued by your suggestion at the end in terms of extra work, where you were thinking about the moisture transport induced by teleconnection patterns. And it just made me curious about, like in the tropics, there's this kind of well-known relationship between column moisture and rainfall, or
Yeah.
I guess it would be cyclones in that case. Has anyone looked at that in the extratropics? I mean, it's kind of is implicit in your idea that there would be some sort of relationship like that.
Yeah, so the paper I was following, or I was kind of using as a guide, they did do some total column water vapor stuff, and they did it during the winter though, and I can't remember if it was like through the, I can't remember if it was just over North America or if they focused over like the Pacific. I really can't remember, but
Sure, that's fine.
no, but
who wrote
that is like I said, there's so much that I wanted to do that I just like didn't have time. But I definitely think having the moisture transport with the results I have, like it would just complete it all and just give a whole different story as to what exactly is happening. And so I wish I could add that. I can't right now, but I do think the moisture would really complete everything for sure. It tell so much more as to what's happening in the large scale.
Well, it would be a whole different mechanism, I think, than anyone has looked at for mid-latitude teleconnections, right? I mean,
Yeah.
it sounds like maybe there's some work, but
yeah, no, yeah, you're right. That'd be kind of cool.
I mean, I don't know. You'd have to show that the mechanism was actually important too, right?
Yeah.
You're gonna be strongly connected to low PV too. That'd be another nice aspect of doing something like that. I bet they're highly correlated. Big moisture plumes are always low PV plumes, at least the notable ones. That'd be
Yeah.
really cool.
Yeah.
Go ahead, Pete.
Okay, a couple more things from the YouTube stream. First of all, Evan says, I think a bootstrap analysis of the frequency and intensity during each phase compared to all phases might have given some additional meaning to the anomaly values. And then he follows up and says, thank you for the answer. Good talk. So that, and then Melissa Breeden says, thanks, Angelica. I'm glad spring is being examined. Did you ever break down your composites by each month? What is the distribution of MJO events? Are there as many in March as there are in June?
Trying to think.
I can repeat any of that if you need me to.
No, I know she asked me if I did it by month. I don't think I did. I don't think I separated it by month. No, I didn't, because when I was filtering or when I was compositing using the RMM indices, I remember that I just took the chunk of March, April, May, June, and I chunked it together, and then I went on it or went through it that way. So I did not do it by separate months. And why I didn't, I think is because that sometimes since it takes so long for the MJ, I mean, it takes about 30 to 60 days to go through its whole cycle, that I didn't like doing it by month. It's like, wouldn't, I mean, that's why that's why I think, which Stephanie can correct me if I'm wrong. That's why I think most of the research and papers done on the MJO do take it by like DJF or MAMJ or whatever, is because since it takes so long to go through all the 8 cycles, if we did it monthly, it may not speak as loudly as if I do it for a whole season. I don't know if that makes sense. Or I don't know.
I'll just add to that. I think it would be really interesting to separate it by month. You would get some of the seasonality of the jet, some seasonality of the storm tracks if you separated by month. But I think that a concern would be sampling. And even though here we didn't add the number of days, which it would be really good to do to see what kind of sampling we're working with in the first place. That would, the more you cut your data, looking at smaller and smaller amount of data, then the less sampling you have. But it would be interesting.
Yeah. I just like the past papers that I had all read, I had always done it by a season. So that I kind of just followed that and did it by a season. But I bet you could find some interesting conclusions if you did it by month. I just didn't.
Does anybody else have any other questions? Okay, great. Well, we are on the hour, so perfect timing. Thank you so much, everybody. Thank you, Angelica, for a great presentation and a lot of really interesting work. Yeah, have a great day, everyone.
Thank you, everybody, for coming.